You know, it's smaller than a postage stamp, but it runs our entire world, the semiconductor. This tiny piece of silicone, it's the product of a massive, incredibly complex, and, as it turns out, astonishingly fragile global system. So what happens when a system like that is pushed to its absolute breaking point? Well, I think we're all about to find out.
To really wrap our heads around what's happening, we need to look at 5 critical pressure points. We're going to explore the explosion in demand for these chips, the staggering complexity of just making one, the single island where the most advanced ones are born, the planetary resources they consume, and finally, how they became a weapon of global power.
So first up, let's talk about the AI demand shock. It's this massive, unprecedented surge in demand that has suddenly put this entire delicate system to the ultimate test.
If you want to grasp the scale here, you just have to follow the money. In a single year, the value of the world's top chip companies nearly doubled, hitting an incredible $6.5 trillion. Now, this wasn't just normal growth. This was a shockwave. And at its epicenter was one single transformative technology: artificial intelligence. But here's the thing. This boom wasn't universal. You can see it right here. The market basically split in two. While the rest of the semiconductor industry did okay, the companies that were fueling the generative AI revolution, they just skyrocketed. This wasn't a rising tide lifting all boats. It was more like a tidal wave lifting a very specific and very powerful fleet.
And this is really only the beginning. By 2028, the market just for AI accelerator chips is projected to hit $500 billion. To put that in perspective, that's more than the entire chip industry was worth back in 2023. The future, it seems, is being built on AI. And that suddenly turns the question of who controls the chip supply into one of the most important questions of our time.
Okay, so the demand is just exploding. But what does it actually take to make one of these advanced chips? I mean, these are arguably the most complex objects humanity has ever managed to mass produce.
You can think of the process as a global relay race. It all starts with design, which is incredibly knowledge-driven. Then it moves to wafer fabrication, which is just brutally capital-intensive. And finally, you have assembly and testing, a phase that's still very much labor-intensive. Each stage needs a completely different set of resources, a different kind of expertise.
And this diagram here, it really just scratches the surface of the true complexity. It is this sprawling, interconnected web of thousands of steps, specialized materials, and unique tools. No single company and no single country has mastered every part of this process. The whole system is built on global interdependence.
Now, deep inside that web, there's one specific process that's become a critical choke point: extreme ultraviolet lithography, or EUV. This is the mind-bending technology that allows us to print circuits with features measured in just a few nanometers. It's absolutely essential for making the most powerful AI chips.
But the challenge here is just immense. A single EUV machine costs around $350 million. It weighs over 180 tons, and there is only one company on the entire planet, ASML, in the Netherlands, that can actually build them. This incredible technological monopoly creates a massive bottleneck for the entire industry.
And that concentration isn't just about the technology, it's also geographical. The vast majority of those priceless EUV machines and the advanced manufacturing they enable are all located in one very specific place.
Think about this. The entire global supply of the most advanced chips really hinges on a single island. Taiwan produces over 90% of them. The processors in our phones, the GPUs training our AI models, the components in our advanced defense systems, nearly all of them start their life on this one island.
So the immediate risk here isn't necessarily a full-blown military invasion. The more subtle and maybe more likely threat is a kind of economic strangulation. A blockade of the Taiwan Strait, which is a vital artery for global trade, would cause just catastrophic disruption, all without a single shot ever being fired.
And even just getting those finished chips off the island presents its own high-stakes trade-off. You could use air freight, which offers speed and security, great for high-value chips, but the cost is enormous. Or you could use sea freight, which is far cheaper, but it takes weeks and is much more vulnerable to disruption. It's a constant, tense calculation for global supply chains.
But the strain on this whole system, it doesn't just start with moving the finished product. It starts much, much earlier, with the industry literally running up against the hard physical limits of our planet.
These chip fabrication plants, or fabs, are just incredibly energy hungry.
A single large fab can consume up to 200 megawatts of power. That's about the same as a small city. And this puts enormous strain on local power grids, especially as that insatiable demand for AI chips just keeps climbing.
Fabs also have a profound thirst for what's called ultra-pure water, water that's thousands of times cleaner than what we drink. A big fab can burn through 10 million gallons of it every single day. This creates immense strain in the exact same water-scarce regions where they're often built, like Taiwan and Arizona. It turns out the virtual world of AI depends on a massive physical footprint.
And you know, the physical constraints don't even end there. The system is also running low on human capital. There's a severe shortage of skilled engineers. It's totally dependent on design software controlled by just a handful of Western companies. And it's facing a growing battle over the raw materials and equipment it needs to function at all.
So when you take all these pressures together, the AI demand, the manufacturing complexity, the geographic choke points, and the physical limits, they've transformed the chip from just a simple component into a central piece on the geopolitical chessboard. What we've seen is a fundamental shift in how nations view semiconductors. For a long time, they were seen as a simple commodity governed by supply and demand. But today they are viewed as a critical lever of national power, something essential for both economic prosperity and national security.
And as a result, governments are deploying a whole new arsenal of economic and political tools. They're using massive subsidies, like the $52 billion U.S. CHIPS Act, to try and build domestic factories. They're imposing strict export controls to deny their rivals advanced technology, and are using access to chips as a powerful tool in diplomatic negotiations.
And all of this brings us to a really fundamental question. I mean, the global semiconductor supply chain is a modern marvel of efficiency. It's a system that delivers unbelievable technology at a colossal scale, but has its very perfection made us blind to its profound fragility?
In the end, it all comes back to this single, tiny object, the product of a globe-spanning, hyper-efficient machine, a system that works perfectly right up until the day it doesn't.
The race for AI is now putting stress on this system in ways it was never, ever designed to handle. It's accelerating the risks of disruption far faster than we can build resilience. The quiet engine of our modern world has now become its most contested and vulnerable frontier.